Okay. Right. So the ER model is a way to pictorially put constraints on a database system. The relational model is what SQL is based on, where relations can be viewed as tables that have columns of certain types, and these tables can have a relationship with each other. This can be by having commonalities between their rows. Let me just go to this screen. So, for example, here is, oh, that's too messy. Let me find a neater one. Sure. So here on the left, we see an ER diagram that is a diagram that shows what the different entities are and the relationship between them. And here on the right is one way of realizing this in the relational model. You can, when I assign the homework on this, you can really do it either way you like. If you want to draw it as a table, or if you want to write it out in the SQL-like language. Personally, I think the written way is easier. For one, you wouldn't have to figure out how to draw tables and arrows. And I think it's just clearer to see everything that's happening. But that being said, if you prefer one way or the other, I'm fine with it. However you like. And now, today we're going to be talking about relational algebra. And what relational algebra is really for is to be able to make queries to a database. So you can define constraints on a database with an ER diagram, and you can kind of map out what that database should look like with the relational model. But once you have the database and you want to start using it in the way that people basically use databases, which is to query them, this is really where relational algebra comes in. And relational algebra, relational calculus, these might sound like scary terms or something, but it's actually all very simple. And or the parts that each part of it is very simple. It can get a little tricky figuring out how to realize certain queries, but that's what our next couple of lectures will be going over. So really, this is about sets. No, actually, if I don't have to write it, I'll just type it. Let me make this bigger. Okay. So we already talked some about sets with ER diagrams, where oftentimes they're depicted using circles or ovals, and you can think about members of the set as being sort of dots inside of it. I will go back and forth between, if I just draw an oval like this on the right, then these dots are implied. I might not draw them explicitly. And the reason for this is when you talk about, for example, if you have a set A and a set B and where they overlap. Sometimes it could just be kind of annoying if you're trying to draw dots and get that working pictorially. So I might simplify things a little bit and just use these sorts of overlapping diagrams. Let's see. Okay. So, sets. I will write, if I just draw one circle like this is considered the world. This is the world of everything that this set is concerned with. And it's depicted by this Greek letter omega. So, for example, this could be social security numbers, or all integers, or dates up to, I don't know, 1, 1. I don't know, from year 1 all the way up to year 2500. All of the days, all of the dates. These are each examples of what this omega could be. And inside of omega, you can have smaller sets, A. So if, for example, omega is social security numbers, then maybe A are social security numbers of, I don't know, people in New Jersey. So this is a subset. So A is itself a set, but it is a set that is comprised of things of a larger set. And you could have, for example, another set, B, that's also a subset. And maybe this is social security numbers of people aged 20. So only people who are 20 years old right now. And A and B are each subsets of the world omega. This is, by the way, a subset is written this way. Well, I'll get to notation later here. A is a subset of omega. So these two sets, A and B, might have some overlap. And this overlap is called an intersection. So these would be people aged 20 who live in New Jersey, what their social security numbers are. There's some basic set operations. Let me scroll down some.
When you wrote A as a subset of omega, is that a C in a line, or is a less than or equal to?
Oh, thank you. Yes. It looks like a C. Yeah. So
Okay.
Yeah. It's a line like that looks like a C with a line underneath it. So, and that's sort of, sorry, my Greek lettering isn't so great, but an omega looks something like that. So, this sign means that A is a subset of omega. So, for example, if omega is a set, let's say John, Paul, and Mary. These squiggly brackets are a way of denoting a set. Squiggly bracket. So this set has 3 elements. And these lines mean the size. Now, if A is a subset of this, for example, A could be John and Paul, then this, A is a subset of omega, holds true. Let's see if I have B equals John, Paul, Mary. Then B is also a subset of omega. Here, A is a subset of omega. But also A is strictly smaller than omega. So the same way that you have a less than and a less than equal to, this symbol works in the same way. If this statement is not true, 2 is less than true than 2, but this statement is true, 2 is less than or equal to 2. So here, A is a subset of omega, and this is a proper subset, or a strict subset. Let me get rid of this. Notation. Okay, so we have using squiggly brackets to denote sets. Each of these things are elements of the set. You can denote the size of the set using these straight lines, and you have subsets and proper subsets or strict subsets. So if you're not sure, you can always use this with the underline symbol. I won't really be asking questions of the sort where this would really have to concern you, but just for the sake of completeness, I want to include it. Okay. So this is called a union, and in this example, let's see. Well, whatever. In this example, the intersection between A and B, it's this part. Oh, I'm sorry. This is union, not intersection. The intersection, let me do this in a different color. A union B means A and B together. So A union B here is everything in A and everything in B together. I'm going to move this down. I wanted to start first with a concrete example. And I'm going to introduce some more math-looking notation. Don't be scared by it. It's actually pretty easy. Okay, so what this is saying, first of all, the squigglies tell us that, switch colors. The squigglies tell us that this is a set. And it's a set where an element is included in the set, x. This is read such that, I should use these same colors. So A union B are elements such that x is an element of A or x is an element of B. Okay, so this is sort of a more strictly mathematical way of writing the definition of A union B. Is there an easy way to do this? I was hoping I could just... Oh, that's stupid. Okay, I'll try to change these colors later. I don't want to get too sidetracked. Okay, so this is going to be one important part of the relational algebra. This is a union. Actually, I think this might make it easier to read later. Union. Okay, after the union, we have the intersection. And this is written with this sort of cap symbol. And so this is elements x, where x is in A and x is in B. Written kind of pictorially, it looks like this. And in our example, this would be John and Paul. Because John and Paul are in set A, and John and Paul are also in set B. Then we have the set difference A minus B. I'm going to write this the other way around. B minus A. So these are elements x such that x is in B and not x in A. The reason why I switched this around is because B holds more elements than A. So B minus A is you remove those elements in B that are in A, and the result is what's left over. In this case, Mary. Oh, don't know what that was. Mary. Wow. Okay. So here, pictorially, if this is A and this is B, this set difference would be these elements. Those that are in B only, not in A. Okay. Actually, I want to move some of this stuff down so I can add some more notation things. Great. So these that I'm numbering, these are operations in relational algebra. So I want to define here another term, disjoint. And that is the case if now I'm writing omega as this box and A and B here. A and B are disjoint if they don't share any common elements. This is not an operation, this is just a property of sets. So I'm keeping it separate from these other things. Okay. Oh, let me go back here. No, I can go down here. No, let's see. I want to try to keep this clean looking, but it is what it is. Okay, so do this example. Let's say A equals 1, 2, and 3. B is 1, 2, 55. Question. Is A a subset of B? So this I'm asking you. You can please type your answers. Okay, it looks like there's some overwhelming consensus. Correct. A is not a subset of B. Although they share some common elements, 3 is not an element of B, so A is not a subset of B. 3 is not. Oh, so here, this symbol is read that X is an element of A. If X, so 3 is an element of A, but 3 is not an element of B. So that's another notational thing. Is not an element of. Oh. Another term is complement. So if you have your world, omega, and an element A, this is the complement of A. So A complement is written, this is one way of writing it. It's the way that I tend to prefer. If you put a line over the set name, then this means everything outside of that set that is still inside of the world. Okay. Let me move this down more because I still have some more general set stuff to talk about. Yeah. There. Okay. Now, we've already talked about this, I believe. But the cross product is all possible pairings between two sets. So here, can anybody tell me what the cross product is between A and B? And in when you're talking about sets, this X here is the cross product. It's not the product. It's not read A times B. This is read A cross B.
Is it what's in the middle of the two circles if they overlap?
No, that is the intersection. So our question is, if this is A and B, is it this? No, that is the intersection. That is written this way. A intersect B.
The element is in both A and B. Would you count it as making one of the pairs? Like, for example, would you do like John, John, or
Yes.
no? Oh, you would?
Yep.
Okay. So it would be John, 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 Paul, John, Mary, Paul, John, Paul, Paul, and Paul, Mary.
Yeah, excellent. Perfect. So you take each of these, so stick with the first element, and then you pair it with the first element in B. You pair it with the second element of B. You pair it with the third element of B. And then you do the same thing for Paul. So everybody gets paired. All possible pairings. So in this case, this would be John, John. And now I'm introducing some some new notation. So the squiggly is a set. This means a tuple. Tuple or tuple. I've heard it pronounced both ways. I usually say tuple. And this is one element. Of the set. All right, so we have John, 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 Paul, John, Mary, let's continue it here. Then Paul, John, Paul, Paul, and Paul, Mary. Okay. Question. What is the size of A cross B? You can either unmute, let's see. 6, 6, 6, 6. Yes, correct. But 6 can be many things. 6 can be 1 plus 5. 6 can be 10 minus 4. This 6 is 2 times 3. So the size of A cross B is equal to the size of A times the size of B. Okay, great. Okay, here's another question. No, this is an example because there's a setup. Let's say A is 1, 2, 3. B is 3 and 4. Try to make that a bit set. All right. Oh, so it's a little bit more clear. A tuple or a vector. Do it this way. So sometimes I'll call this thing a tuple. Sometimes I'll call it a vector. If it's a vector, then in either case, the dimension is 2. Here. Okay. So, question. Is A a subset of A cross B? Is A a subset of A cross B? Okay. There still seems to be a consensus. No. Correct. Answer. No. So, for example, here, if A is John and Paul, each of these, an easy way to get to the answer is this is still a tuple, or it's still a vector, but it's this is sort of implied, putting these in parentheses. If you if it only has dimension 1, then you can usually just omit those. But yeah, this is of dimension 1, and each element of A cross B is of dimension 2. So they are not A is not a subset of its cross product. Okay. If there's anything else I should mention before moving on. Yeah. I'll add something here. No. In fact, A is disjoint from A cross B. Just to use the term that we just talked about here. If two things are disjoint. Okay. So these three are all pretty straightforward. And all of these work on the same kind of tuple. What I mean by that is that first of all, the dimensions have to be the same. So here we can discuss, for example, B minus A, because each of these are sets of one element each, and they're in the same world, omega. Okay, so because each of them come from the same world, then they all work on the same kind of tuple. That's what I mean by that. Okay. So a different kind of operation is the projection. Here, the projection is written with pi, because that's the letter P in Greek. So projection pi. And what this does is turns many coordinates into few. So this is probably easiest seen with an example. Pi keep first coordinate and let's say it works on this set. First element is 1, 2. The next is 2, 3. The next is 1, 5. And next is 3, 4. So there's a couple things to notice. First, the projection here has a name. Okay, if you were to type this, that's very small. Oh, come on. Let's make it even bigger. If you were to type this, then you can type it this way. Keep first coordinate. Okay, using this little underscore, that just means a subscript. This is just in case you have like a homework or something, and even then, if you don't know how to insert pi, you can just write pi. That's fine, or p, whatever. I mean, so long I understand what you're saying, it's okay. But if you don't want to handwrite your answers, that's just a quick note. So this pi function, it's a function, and it takes as input a set. And it outputs a set. Here, this set would be 1, 2, and 3. Okay? Now, there's one thing to notice here. So I'm calling it keep the first coordinate. What that means is for each element, so this element, this element, this element, and this element, I'm going to keep the first coordinate. So there's a 1, there's a 2, there's a 1, and there's a 3. So sometimes students are inclined to maybe write something like this. So you're taking the first coordinate of the first element, the first coordinate of the second element, the first coordinate of the third element, and the first coordinate of the fourth element. But these are actually the same. So with sets, repeated elements are just not included. I mean, it's not wrong, it's just sort of annoying to have it there. It's redundant. So if you have a repeated element, you can just get rid of it. Also, with sets, order doesn't matter. So this is the same as this. It's getting a little busy. And then these two are also the same because order doesn't matter. So think of sets as just like balls in a bag. You can shake the bag and the balls will change their position, but each, like, the bag still has the same balls inside of it. And Eric, yes, both of those are the same. You can write it with those parentheses if you like. It's not incorrect. It's just sort of easier to write it without it most of the time. But whatever you like. If you want to be consistent, sure. Yeah, generally, mathematicians will just drop it because they want to be consistent, but they're also lazy. So this is it. Then it's just called a convention. Okay. So, any questions about what a projection does or how it works? Can you also have 2, 1, 3? Yes, you can. Yeah, it's the same thing. So those are 3 elements, 1, 2, 3. Any permutation of them is equivalent. All right. So the one main takeaway from this projection that makes it different than these 3, the union, the intersection, and the set difference, is that here, A union B, the type of A and the type of B have to be the same. And the result is also of the same type. Where here, with a projection, it's taking in a set where each element is of dimension 2, and the result is a set where each element has a dimension 1. So this is what I mean by it turns many coordinates into few. This is like if you have a table with a bunch of columns, and you can project the whole table with, let's say, 10 columns into a table with 2 columns. Okay, it's just sort of focusing on particular coordinates. Okay, after this, I'll give myself some more room. Okay. After this, we have the select operator. And that's written with a symbol that looks like this. It's not exactly an O. It has this sort of, I don't know, tick above it. And this is read as sigma. Okay, so pi is chosen because it's a Greek letter that starts with P for projection. This Greek letter is chosen because it starts with an S, as select does. Okay, it's read sigma. This is the lowercase sigma. You might be aware of the uppercase sigma that's used for summation in regular algebra. But anyway, relational algebra has the lowercase sigma. And this outputs a subset. Keep, tuple, or not. So, for example, sigma the second coordinate is even. And so this is also a function, and it's a function that takes a set as input. And let's see if I can save time and just use the same numbers here. Why? Cool. Close enough. All right. So the way that this function works is it takes a set, and again, it applies this function to every element of this set. So here, let's see. Before I write the answer, can some people write down what they think the output of this would be? Sorry. So my question is, what do you write here? Okay, good. We're getting some different answers. That also makes it more interesting. Yeah, good. So Jamie, Tushar, and Brian are all correct. So is Sanjana. Yeah, just missing the set notation here. So this takes each element, and it's not a projection. The projection reduces the number of coordinates. This will output a set with elements of the same dimension. So this would, this passes the test. The second coordinate here is even. This does not pass the test. This does not pass the test. This does pass the test. And so you have two tuples that pass the test. Okay, so that's a select. All right. Okay, here's another question before I move on to the next function. Matthew wrote this, 2, 4, as his answer. It's not what the select does, but how... Let's see, I'll paste that set again. Given this set, how to get the set 3, 4. I'll give you a minute. Sorry, Danielle. Are you? Which function is this? Pi or sigma? And everybody else, keep giving answers if you can. Sigma. Jamie, no, you're not getting 2, 4. Oh, I'm sorry. You're getting 3, 4. Oh, I'm sorry. Yeah, you're right. 2, 4. No, 3, 4. 3, 4. If you're still working, can you just type still working? Okay. How to get just the last element? No. If I wanted just the last element, I would write that this way. Because that's an element of dimension 2. I want a set with 2 elements. Element 3, element 4. Sigma sum of coordinates equals 7. Okay. Let's see. Okay, so I'll just start answering some of these. Jamie said later, never mind, I think. Yeah, ignore my answer. Matthew, pi, keep second coordinate if x is between 3 and 4. So, pi, the problem is that with your if statement, you're on to something there, but that's not something that the pi function is capable of doing. I guess the same thing for Toyin's answer here. Pi keep second coordinate if first coordinate greater than equal to 2. So the if part of this statement is where the pi kind of falls apart. It's not capable of doing that. Pi keep second coordinate of every other element. The same thing with Sanjana. Of every other element. So the set here, sets don't have order. So saying to do something to every other element is something you shouldn't do with sets because order doesn't matter. If I give you a set and then you apply something to it and then I mix up the numbers in the set, it's the same set, but now the every other element part might screw things up. Can you select positions with pi? No, you can't. Okay. So good answers. You can, the answer here is that you combine functions. We have a projection and a select. So first of all, we can select where the second, well here, I can just copy this whole thing. So this select is part of the way there, but the dimensionality is wrong. Do this. Give myself some more room. Okay, so we know that this will return the same thing up here. I just copied it and pasted it. But for this result, we only want to keep, let's see. Select if the, well, actually, is there a better combination here? So here, this won't work if it's even. I'll say if the second coordinate is 3 or 4. So what this would output is 2, 3, and 3, 4. But we don't want the whole tuple. We just want the second element here. So you can then apply a projection to this, which is keep second coordinate. So that is the same as taking this and applying pi keep second coordinate. And this will give us the set 3 and 4. Okay, so we first apply a select to sort of filter out just those elements that we care about. And after that, we do a projection to keep only the parts of the tuple that we want. Does this make sense to everybody?
I have a question. So you know how you said you like select 3 and 4 when you used I think it was sigma. Can you also do that for pi? Like you could just say second coordinate is 3 or 4.
I'm sorry, say that again? I didn't quite.
Like you know how you selected you said second coordinate is 3 or 4.
Mm-hmm.
Like can you do that for pi and sigma, both of them? Like you can't do if statements, but you can say that if it's 3 or 4, that works.
Oh, so that's basically what the select is doing. The select works like an if statement.
Okay.
Yeah, I'll keep the elements if some condition is true. So some other people's answers that were saying do pi of something something if whatever, if they replaced that if with a sigma, just literally took the word if and replaced it with a sigma, then those answers would probably be correct.
Okay, that makes sense. Thank you.
Sure. So the sigma here is acting like an if statement. And this pi is working like, I don't know, a print statement. You only want to print, I don't know, certain columns. And this if statement means keep row if satisfied. I don't want to necessarily talk about rows and columns right now because really this is rows and columns don't exist in relational algebra. Relational algebra just works with sets, but if this is sort of where we're going with this. So just to kind of give you a heads up, but I'm going to erase this just to keep this relational database or the relational algebra lecture kind of self-contained, not mixing this with other things. Okay. And so this is really what where things tend to get tricky. Individually, each of these are very straightforward. The union, intersection, set difference, projection, select, and I'm going to go through another one that's very easy. But when you start combining them in this way, that's where it can take a little bit more thought. And even then, some examples are easy, other ones require a little bit of thinking. But we're not going to be getting into any of those types of examples today. Oh, pi keeps second coordinate, then set difference of set 2, 5. Yeah, Lydia, yeah, Lydia, that works, I guess. But then the question is, where is the set 2, 5 coming from? It's a bit of a wonky way of doing it. Technically, I guess it's kind of right, but yeah, you're kind of pulling something from the ether to get things to work. So, all right. There's rename. And so this is written with this letter that, as you might have guessed, is the R in Greek, and it's pronounced row, like row, row, row your boat. And that's all it does. It's pretty uninteresting. So, for example, let me cordon this off. Okay. Well, actually, now I am going to be talking about relations. I lied. Sorry. For example, before we had a relation with social security numbers, but maybe you wanted to rename those to be my social security numbers. And this takes in a relation, and it will output a relation. So this is the relation as in the relational model. So that is sort of renaming a column. Here, maybe if I didn't like student ID, then I could do row student, I don't know, SID, and I could just name it student underscore ID. If I applied this rename to enrolled, the enrolled relation, then the result would be the same relation, except this would now be named student underscore ID. Okay, it's just renaming a column. Pretty uninteresting, but you need it. go back here. Okay, and that is basically it. There is still something called a natural join that I will cover next class. And really, you don't need a natural join. Everything that I've covered so far is enough. Oh, actually, sorry, the cross product should be included in this list. You need that. I'll call it 0. Oh, sorry. People probably don't like counting from that. So that is it for today's lecture. We'll continue next time. I will quickly go over these again, and the last one, a natural join. But yeah, you can actually replace a natural join. A natural join is just a cross product mixed with a select. But yeah, we'll get to it then. See, does sigma support functions such as x between 3 and 4 inclusive? Yes, it does. Yes, it does, Matthew. Okay, great. So you can expect in the next day or two a homework assignment, and it'll be due in a week. I'll try also to give some type of practice. The homework assignment will just be on ER diagrams and the relational model. If I give a practice assignment, it might be something dealing with these, with relational algebra, but relational algebra will not be on the homework. Okay, great. Yeah, everybody have a nice weekend.